Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. During this session, we are going to learn another type of register called as counter. From the previous sessions, you might have understood the significance of flip-flops in sequential circuits. These flip-flops help the circuits to store or memorize the previous values, and that is why they are known as the memory elements of the circuits. Here we are going to discuss about counters, another sequential circuit which makes use of flip-flops. Counters are judicious applications of registers because they are making use of the memorizing capability of the flip-flops to the fullest. In the introductory sessions of flip-flops, I had mentioned about the usage of memory while counting. Hope you are able to recall it now. The basic criterion for counting is that it should be able to remember the previous value that has recorded. To store this value, we need to have memory elements, and that is why we say counters are registers which fully utilize the service of flip-flops. Now, you might have got a rough idea of counters. Let us dig inside to understand better. What are counters? According to the standard definition, counters are sequential circuits that goes through a prescribed sequence of states upon the application of input pulses. Let us see what this definition implies. It is said that the circuit goes through a prescribed sequence. What does this indicate? Suppose you are asked to count from 1 to 10. I know very well the order of the numbers that you are going to say while counting. How do I know that? Because the numbers and their order are predefined. That is why it is said that the counters go through a prescribed sequence of states, and these states are already well known. It looks like that things are pretty simple because we know the states the counters is going to go through well in advance. Now, what exactly the counter is going to count? It is going to count the number of clock pulses that have arrived at its clock input. Let us see how this is being done. Let us take an example of binary counter, which is the simplest and straightforward counter. Before moving into the technical details, let us learn how the counting is done using a simple example. Suppose your counter is a 3-bit counter, it can count from 0 to 7. Then, because 3 bits will have 2 cube combinations, which is equal to 8. Look at the table, it shows the binary values of each number from 0 to 7 in 3 bits B0 to B2. Let us have a serious study of the transition of bits while the counter progresses in counting. The decimal 0 is indicated as 000 in binary. The decimal 1 is 001 in binary. What has happened here? To change from 0 to 1, the least significant bit or LSB is toggled or complemented. That is, the rightmost bit became 1 instead of 0. So, please note that to count in binary, you need to toggle the rightmost bit. So, to go to the next number decimal 2, shall we toggle the LSB again? What will happen if you toggle the previous value 001 again? It will turn back to 000, which is equivalent to the decimal value 0. Toggling the last bit alone did not create a favorable impact. We did not progress in counting, rather one would say we counted down. So, now we understood that just by toggling the last bit you cannot progress in counting. What shall we do then? After toggling the LSB, you need to check whether the result is 0. If it is 0, then you must propagate the toggling effect to the adjacent left bit. So, consider the binary number 001 again. Toggle the LSB first. Now you got 0, 0, 0. The toggling result is 0. Now propagate the toggling effect to the next bit. Then the bit B1 becomes 1. Now the binary number becomes 0, 1, 0. This is equivalent to the decimal number 2. Now count again. The binary number is 0, 1, 0. Toggle the last bit. The B0 was 0 and changed to 1 now. Since the result is not 0, you don't have to propagate the toggling effect. You can stop it there. The resultant binary number is 0, 1, 1, which is equivalent to the decimal number 3. Count again. The current value is 0, 1, 1. Toggle the LSB, it becomes 0. What to do now? Propagate the toggling effect to its adjacent left bit. Now the bit B1 becomes 0 since the toggled output is 0. Propagate the toggling effect to B2. Now B2 turns from 0 to 1. Now we can stop the propagation of toggling effect. What do you have right now? You got the binary number 1, 0, 0, which is equivalent to the decimal number 4. Now you might have got an idea what the binary counter does while counting. Can you complete the counting up to the decimal number 7 using the same approach? Please do it so that you will be thorough on the toggling and propagation operations that the binary counter performs while counting. This was an example of 3-bit counter and you could count from 0 to 2 raised to 3 minus 1. In that case, if you have an n-bit counter, then what you can count? Count from 0 to 2 raised to n minus 1. Since there are n bits, you need to have n flip-flops in the counter. Because all the values have to be stored inside the circuit at the same time, and understand that it is the clock pulse that is going to trigger the toggling effect of the counter. Now, let us look into the technical details of the counter. The counters are of two types, synchronous and asynchronous. What is the difference between them? In synchronous counters, the flip-flop inside change its state upon the input of the same clock pulse. That is, the transition happens at the same time. But in asynchronous counters, the transition of the first flip-flop alone is caused by the clock pulse and the remaining flip-flops are not affected by this clock pulse. Instead, they are triggered by the transition or the state change that occurs in other flip-flops to which they are connected to. Let us see the asynchronous counters first. Binary ripple counter, it is a good example of the asynchronous counter. It consists of a series of T flip-flops or JK flip-flops with J and K input kept at the level 1. Look at the diagram. It is a series of JK flip-flop which have kept both its input at level 1. There is an incoming clock pulse to the LSB flip-flop in the left, and for all other flip-flops, the clock is connected to the output Q of the previous flip-flop. Recall that an asynchronous counter changes its flip-flop state at the transition of the other flip-flops to which they are connected to. That is why in the design of the ripple counter, we are connecting the output Q to the clock pulse of the adjacent higher order flip-flop. You can see that the output of the LSB flip-flop triggers in the next higher order flip-flop and its output triggers in the next higher order flip-flop, and this process continues till it reaches the flip-flop at the most significant bit. Did you notice a small circle in the clock input in the figure? This signifies that the circuit is a negative edge triggered circuit. The clock pulse triggers the circuit when the pulse goes from high to low state, not when it goes from low to high state. Now, there are 4 flip-flops, so it can count from 0 to 2 raised to 4 minus 1. That is from 0 to 15 in decimal. Let us understand how this binary ripple counter works. Before that, you need to learn the rule of this counter. every time the flip-flop goes from 1 to 0, it complements its adjacent higher order flip-flop because the circuit is a negative edge triggered circuit. Now let us start. The inputs to all the flip-flop in this circuit are always 1. We have learnt that the JK flip-flop toggles its current state when its both inputs are at the high state. Recall the toggling and propagation operations that we discussed in the beginning of this session. Assume the first clock pulse has arrived. During the trailing edge of that clock pulse, the flip-flop at the LSB toggles its value and it triggers the rest only when the clock pulse goes from 1 to 0. What happens now? The LSB has gone from 0 to 1, not from 1 to 0. So, the rest of all flip-flops will not get triggered and will remain in its previous state, resulting in the binary value 0, 0, 0, 1. Now, apply this logic at the arrival of next clock pulse. It triggers the LSB. Now, the value at LSB is 1, that will turn to 0. This will trigger the next flip-flop and it toggles its value from 0 to 1. Now, toggling does not propagate because the last change was from 0 to 1, not from 1 to 0. Now, we have the binary value 0, 0, 1, 0 as the output. This process continues for every clock pulse. Let us look into one more scenario. The previous state is 0, 1, 1, 1. What happens when the clock pulse arrives? It toggles the LSB. Since it is changed from 1 to 0, it toggled the next one. And the next bit 1 and the next bit 0, 2, resulting in the value 1, 0, 0, 0. Did you notice that the flip-flops are changing one at a time and the signal propagates through the counter in a ripple fashion? That is why they are known as ripple counters. Since they are counting up, they are also known as binary up counters. Now, we shall look into the one more state of the counter. What happens when the counter reaches the binary value 1111? In decimal, it is equivalent to 15. That is, we have reached the upper limit of the counter. We cannot count further. What happens then? The clock pulse has arrived at the LSB, toggles the 1 in the LSB to 0 and triggers the second higher order bit 1 to 0 and then trigger the toggling of the third bit to 0 and finally triggers the toggling of the fourth bit to 0. Now, the state of the binary counter is 0, 0, 0, 0. Or in other words, when the ripple counter reaches its maximum limit, it resets itself in the next pulse and becomes 0 to start fresh with counting again. Now, we shall move on to the next type of asynchronous counter, binary down counter. The counting can be done in the reverse manner using the binary down counter. It can be constructed by making few changes in the ripple counter. When we were counting up using the ripple counter, the output was taken from the Q terminal. To count down, you should take the output from Q dash. The logic is very simple. You are starting from 0, 0, 0, 0 in the up counter and its complement 1, 1, 1, 1 is the starting point of the down counter. To get the complement, we are using the Q dash terminal of the counter. The procedure is the same as the previous ripple counter. Start toggling at the LSB and toggling should propagate to the next higher order bit, but with a difference. The signal propagates when the bit changes from 0 to 1. Now, to count down, you should trigger the flip-flop when the bit value goes from 0 to 1. So, in order to trigger the flip-flop while the level changes from 0 to 1, we should have positive edge triggered flip-flops. In summary, To convert the up counter to the down counter, do the following. Make the flip-flops trigger at the positive edge of the clock pulse and obtain the output from the Q dash terminal of the flip-flop. It is time to see the next type of asynchronous counter, that is BCD ripple counter. The term BCD stands for binary coded decimal. You have already studied this. This is a digital code used in computers where each digit in a decimal number is coded as its 4-bit binary equivalent. Suppose the decimal number is 23. Then to convert it into BCD code, 2's 4-bit binary equivalent and 3's 4-bit binary equivalent is written. Thus, the decimal number 23 is equivalent to 0010, 0011 in BCD. So, for a counter working in BCD mode, it should count only up to 9 and should return back to 0 in the next clock pulse, because BCD assign codes for each digit in a number and digits range is from 0 to 9. In other words, BCD is a non-positional coding system. This is a challenge that we are facing while designing the BCD counter, and the design of such circuit is not easy. It requires good logical skills to design a BCD circuit. The figure shows one such design of the BCD ripple counter. The previous counters used the toggling and propagating actions to perform the counting, but in a BCD counter that is not sufficient enough to bring a desirable outcome. Now, remember, a BCD counter need to return to 0 once it reaches the value 9, or in other words, after 1001, the binary equivalent of 9, the BCD counter should return to 0000. According to the logic diagram shown here, we need to have the following conditions satisfied to bring the desirable result. There are 4 conditions to ensure the toggling in proper manner. They are: the first condition, Q1 is toggled on every trailing edge of the clock pulse. This step is exactly similar to the way the other counters are working. Then the second condition, Q2 is toggled if Q1 goes from 1 to 0 and Q8 is 0. Then the third condition, Q4 is toggled if Q2 goes from 1 to 0, and the fourth condition is Q8 is toggled if Q4 and Q2 are 1 and Q1 goes from 1 to 0. These are the conditions for toggling. Now, you need to define the logic to reset the counter. For that, you need to follow 2 more conditions. The first one, Q2 is set to 0 if Q8 is 1 and Q1 goes from 1 to 0. Second one, Q8 is cleared if either Q4 or Q2 is 0 and Q1 goes from 1 to 0. Now, what are these Q1, Q2, Q4 and Q8? They are the output of the circuit. They are named so to indicate the binary weight of the corresponding bit in the BCD code. Let us simulate the working of BCD counter. Initially, the value is 0000. At the arrival of first clock pulse, the LSB turns to 1. Here the first condition is met. No other conditions are applicable here. So, the output is 0001. In the next clock pulse, the LSB is toggled, and since LSB is going from 1 to 0, Q2 gets toggled because it satisfies the second condition of toggling. In the next clock pulse, the value turns to 0011 because only the first condition is satisfied. The next clock pulse is crucial because as per the conditions, the outputs Q1, Q2 and Q4 needs to be complemented. I have summarized the counting of BCD operations in the table. The toggling conditions from 1 to 4, if they are valid and satisfied, a tick mark is given here. else it is mentioned as not applicable. The clearing conditions are also given in the table. You can easily make out that clearing happens only when the BCD counter reaches the highest value. Let us see what happens when the register is at the value 1001 and the next clock pulse arrives. The LSB is toggled, turning the 1 to 0. Since Q8 is 1, then you need to set Q2 as 0, and finally the Q8 is set to 0. Because the Q4 and Q2 are 0, also the Q1 just turned from 1 to 0, and the state of the counter becomes 0 0 0 0. That is how the BCD counter works and resets to 0 when it reaches the value 1001. This BCD counter is also known as the decade counter, since it counts from 0 to 9. If you want to count from 0 to 99, then you need to have two BCD counters connected in cascade. Similarly, multiple decade counters can be constructed by connecting the BCD counters in cascade, and one counter per digit will be used to convert it to the BCD code. That's all about the asynchronous counters. To summarize, we started with the discussion on significance of counters. In this session, we handled asynchronous counters, in particular binary ripple counter and BCD ripple counter. Let me conclude now. We will meet in the next session with the topic called synchronous counters. Thank you for watching. Bye.